Hello, everyone. I'm Beatriz Tucci, and today I'll be talking about. Do you hear me well? It's a bit weird. Okay. About how we can do simulation-based inference using LEFTfield, which is a perturbative Ford model that we will explain in detail soon. So the way that we usually do inference, sorry, I'm trying to figure out how this. The way that we currently do inference in cosmology is basically by compressing down our observation of galaxies to some meaningful data vector, for example, per spectrum by spectrum. And then we define a likelihood for our data vector. And then we can do MCMC to obtain the posterior for cosmological parameters. And for that, usually we have to assume an analytical form for the likelihood. For example, if it's Gaussian distributed, we have to determine the covariance of the data vector. And also we need to have a theoretical prediction of how this data vector depends on cosmology. And the way that we do that is by using this, the effective field theory of large-scale structure and the bias expansion. And the main idea here is that we are restraining ourselves to the large scales where we have perturbative control. And then we know that galaxy formation on large scale should obey equivalence principle, and we can write a bias expansion with this bias operator. And with each of these bias operator, we have a free parameter. And we also have to account for the stochastic effects as well. So if a small scale fluctuations couple and form a large wavelength MOV, and this have their own set of free parameters. All of this just to say that to obtain the posterior cosmological parameters, we have to marginalize over these bias parameters. And all these parameters are usually correlated. So in principle, you want to have a data vector that allows you to break the degeneracy of cosmology and bias parameters. And the state of the art for doing that is combining the galaxy power spectrum and bispectrum. This has been applied to real data ready to do full shape analysis. And let's say, for example, that we choose certain configuration here. The dimensionality of our data vector is going to be around 700 when we combine power spectrum by spectrum, which is doable, right? However, if you think how we can include more information, maybe you can go to the galaxy trispectrum. The biggest problem here is that the dimensionality grows very, very quickly. And then it becomes very cumbersome, for example, to estimate the covariance, to measure this object, to model this object, and also to, you can start worrying whether, for example, your Gaussian approximation is still valid for the likelihood. So this leads me to the first part of my talk, which is simulation-based inference. And this allows us to circumvent some of the issues that I just raised. So I will take some time to explain how this works in practice, since most people think of it of like a black box, and it's actually not. The main idea here is that instead of us now writing analytical likelihood for our data vector, we're instead going to have a simulator that reproduces the data we're interested in analyzing, that takes as input the parameters of interest and produces realization of our data vector that we're interested in using for analyzing. So we're using here an implicit likelihood and not assuming anything of how this data vector is distributed. This allows us to take all the moments of the distribution at once, not only the covariance, but also higher order moments. We also naturally implement a parameter-dependent covariance, right? Because we're calculating at each point in this high-dimensional parameter space. And also allows us to use, for example, summary statistics that don't have even a tractable or a good analytical approximation of how this is distributed. And for cosmology, why this is useful, well, we can choose any summary statistic that we want. So in principle, we could get more information if we're doing things correctly. We don't need to worry about doing cumbersome covariance calculations. And also, in principle, it should be more straightforward to model systematics and also the mask by just inputting directly in our simulation. So let's take here an abstract example of simulation-based inference. We sample some parameters from the prior, and we have the simulator that generates samples that should resemble the data that we're interested in analyzing, right? And then we can compress this down to some lower dimensional summary statistics. We do the same thing to the real data. And because we have the simulator, we can do this 1, 2, and n times, right? At the end, what we have is a set of pairs of parameters and data vectors. And if we simplify this and say, and the question here is how then we get to the posterior from this discrete set of samples. Let's simplify this even further and say that our theta is one-dimensional and x is one-dimensional. And then again, we sample the theta from Repiro, calculate 1x, and each of this point here will be one of this pair of simulations. And the question now is how we obtain the posterior from that, right? The most simplest, actually the first simulation-based inference method that was proposed, this doesn't even use a neural network, was approximate Bayesian computation. And the idea here is that, let's say that your observed x is 1 here, right? So you can define a metric in between your simulated data and your observed data. And you, let's say, for example, could use the chi-squared or something like this, or L1, L2 norm. And you accept all the samples for which this matrix is smaller than a certain threshold epsilon. And in principle, in the limit of epsilon going to 0, this recovers the true posterior. And then you can estimate the posterior like this without using even neural networks. But the problem of that is that the complexity of that grows very quickly with the dimensionality of the parameter space and the data vector. And you are basically throwing away all the simulations here that you used, right? And in principle that you don't know if they're going to be useful or not. So it was later proposed to do what is called neural density estimation. A particular case of it is neuroposterior estimation, where now you use a neural network to sort of interpolate in between this parameter space. And then you can use a neural network to learn a model, for example, for the conditional of theta given x, right? So now from this discrete set of samples, you have a model where you can evaluate this probability or sample from this probability function in a region in this parameter space. And now you're using all the simulations that you needed, that you generated to estimate this posterior, and this is really much more efficient than ABC. In the beginning of my PhD, I was trying to use ABC, and this never converged. So this is very useful technique here. And after we have this conditional, of course, you can evaluate this at any x. So you just evaluate this the observed x, and you have your estimated posterior here. Mm-hmm. So can you sample from this kernel density estimation? Okay, I'm not exactly sure. So this was proposed because basically you can sample and evaluate from this probability density. And I remember reading that the other methods didn't allow to do that. But for example, mixture Gaussian density, where like you basically model the posterior to be a sum of Gaussians, this works. Yeah, this is the same. It's just that it's more flexible. Like in the original papers for their set estimation, they show that more complex distributions usually were easier to achieve by using a neural network. But yes, you can also do. Exactly. Yeah. Yeah. Maybe you need less power. No, I'm not sure this is true. Mm-hmm. Yes, the X is the data vector. No. This is summers. Yeah. Oh, this compressions, for example, so here you can see it's a triangle in a line. It's like the power spectrum by spectrum, let's say, concatenated. Exactly. Yes. It's just any summer statistic. Yeah. No. I mean, this is the, so I was trying to do something abstract here, right? But let's say we generated a cosmological density field delta G here. We compress this down to some lower dimensional summer statistic. You can do SBI directly with this, but the big problem is the dimensionality of this, and there are new techniques to do that. But the standard technique normalizing flows suffers from curse of high dimensionality. So you want to compress this to some summer statistic. Something that people do is you put yet another neural network to compress this neural network compression, right? And you can learn your summer statistic, and because and then you do SBI on this latent space, and because even if you don't know what is the summer statistic, you can do SBI because, I mean, it doesn't have to be Gaussian distributed or anything, right? So. Mm-hmm. Oh, this is a very interesting question. And I mean, we're still, so basically we are one of the only groups doing this with the perturbative Ford model. So in principle, you are taking kind of incomplete loop contributions of the endpoint functions, right? If you're doing endpoint functions analysis. And you have to be careful to see if this is still respecting perturbation theory, right? If you had higher order terms, if this is not gonna break down. And still an area of research, is a new way of doing things, but in principle, if you're doing things correctly, and we hope this to work. It seems it's working some cases, still analyzing, but I'm gonna get to that soon. Yeah, maybe I'm getting ahead of myself. Anything else? Um, I just want to do a parenthesis here because sometimes when I talk about this, people think of also emulators, right? The main difference from simulation-based inference and emulators is that for emulators, you also use a neural network to sort of interpolate, but you need just the mean of your summer statistic as a function of theta. So you basically don't care about this scatter here, right? You just need the mean of the power spectrum, let's say, as a function of cosmology. And then you input that in your likelihood, and you can do explicit likelihood inference faster, right? And this is much easier to do because you're just estimating the mean. While for simulation-based inference, you are really here estimating the full probability density, right? You're not just learning the mean, but the covariance and even the higher order moments as a function of really all the cosmology. So that's the main difference here. And this should be interesting for inference because then, again, you're not assuming that the likelihood is Gaussian or anything like this. So how do neural density estimation work in practice? There are several methods for doing neural density estimation. The most commonly used ones are neural posterior estimation, neural likelihood estimation. The difference here is that you're gonna have a neural network model where it has the trainable neural network parameters that we are gonna denote by phi here. And what are those? These are like the weights and bias of the network, right? So it will depend on the architecture that you use and so on. And once you train this model, you can have the posterior by just evaluating your model at the observed data x naught, as we just saw in the diagram. If you instead, for example, is interested in estimating the likelihood, then you are gonna train a model for the condition of x given theta, and then your likelihood estimated likelihood is just gonna be disevaluated at observed data. And then you have to do an extra MCMC step to obtain the posterior. But again, here you're learning a likelihood that has not only the covariance, but higher order moments as well. So let's see how we actually train a model. For training a neural network, you need a loss function, and this is where the magic happens for simulation-based inference. The loss function is the expected value of the prior of the KL divergence between your target density and your model that you're trying to train, right? KL divergence is a metric in between probability distributions. And what this is saying is that you want to minimize the distance between your model, right, that you're trying to train, and your density that in principle you don't know the form. And it's a bit weird because it seems that it's entering the loss function, the thing we are trying to estimate, right? So it's a bit, seems a bit weird, but if we open this to see what's going on, this is the definition, basically, expected value of the prior, KL divergence. And what we have to recognize, so first of all, what we do is just recognizing that the joint probability is this product here. So we wrote both of them together. And because we are minimizing this with respect to the trainable neural network parameters phi, what happens is that the part that depends on the target density that we don't know is just a constant over the neural network trainable parameters. So at the end, the loss function that we want to minimize is independent of this target density that we don't know. And still you are minimizing the distance between your model and your target density. And finally, you just approximate this by the Monte Carlo estimate of this expected value. And this is where our simulations come in. So you are basically gonna do a stochastic gradient descent and minimize this loss function over batches of your simulation. And that's how this is done. Yes, over the prior. Well, basically because, so in essence, you can put whatever you want here, right? In the loss, this is like, you can do whatever you want. And at the end, we kind of want to use the simulations that we have. So we are sort of integrating over some region in parameter space that we think that it makes sense our model to be lying on. Yes. Yes, it does, because then at the end, what is going to enter here are the data vector and the theta that and the theta was sampled from the prior, right? So if you use a different prior, it's going to be completely different, like not completely different, but if your prior is, for example, smaller than your posterior, then it's going to be completely different. If it's wider, in principle, if you use enough simulations, then it should be similar at least. Yeah, this is an interesting question because like our prior in simulation-based inference is also our part of our training data, right? So you, at one hand, need to have a lot of simulations around the region where the posterior has high density, right? But at the same time, you kind of want to have uninformative priors, right? So this is one of the greatest nightmares of simulation-based inference, really, because yeah, you need to have converged posteriors, right? You don't want this to also depend on the number of simulations used or the priors. So you have to be really careful about this. What people usually do is the sequential approaches where you start from a very wide prior and then you find the posterior with just like a reasonable amounts of simulations. And this is usually larger than true posterior. And then you use this as the proposal for the next round. And you'd go sort of accumulating until you converge to the actual distribution. This is something that you can do. yeah, I mean, it's also this MCMC, right? And usually how we write this model is by using normalizing flows, as I mentioned in the beginning. And the idea here is that you have a complex distribution, P, and you want to sample or evaluate this distribution. And if you can basically do a sequence of transformations from this distribution to a Gaussian distribution. And a Gaussian distribution, you know how to sample from it and you know how to evaluate. And your neural network is going to learn this sequence of transformations here. So that once this is learned, you can just sample or evaluate here your Gaussian distribution and send the samples, for example, through the sequence of transformations. And then you can have samples from the target density that you're interested. There are some caveats here. So these transformations have to be easy to evaluate. So we use like triangle or Jacobians. And also you want to have an expressive transformation. That's why you use a sequence of them. And here is a movie of how this works. This is like you start from a 2D Gaussian, as you saw, which is like our base distribution here, the normalizing flow, right? And then through a sequence of these transformations, you transform it to the two-moon distribution, which is one of the benchmarks used for normalizing flows, for example. So yeah, you can go from this simple distribution where you just have samples to the actual distribution. So now we understood how to use these pairs of parameters and X to obtain the posterior at the end using neural density estimation. The question now is how we apply this to cosmology, right? I have a small parenthesis here, why this is interesting for our case. So I have here plotted for a different case, the distribution of the power spectrum measured in a simulation. And distribution here is just like fixed parameters and changing the initial conditions. And in gray, it's the Gaussian distribution. And as expected, you can see that for very low wave numbers, K, you have a deviation from a Gaussian distribution. And this is because of the break of central limit theorem on the very large scales. You can see that this is very small, right? And this is also happens that for the galaxy bispectrum and trispectrum. Here, plotting the colored ones are the actual distribution that we measure. And although this deviation is small, my point here is to say that you don't have to be worried about these things. So you can just use the summary statistic that you want to do cosmological inference without having to worry whether, for example, if you assumed a Gaussian likelihood here would be assuming that these curves are gray, whether this will impact or not your cosmological inference, right? This is the nice thing of SBI. And we tested to see if this made any difference for sigma 8, and for the cases we saw, it didn't make much difference. But again, you don't have to worry about this. So let's talk about now LEFTfield, which is the Ford model that we use to do cosmological inference. The idea of this Ford model is that we first start sampling cosmology from the prior, and then we can construct a grid here. Lewis, or like if you're ignoring primordial Gaussianity, this grid will be Gaussian. And then the size of this grid is going to be given by lambda. And this cutoff has to be smaller or equal to the linear scale of your theory. And then after we sample these initial conditions, we can evolve it using an LPT. We can use nth order LPT to obtain the final matter density field. And then, for example, for the William bias expansion, what we do is just construct the bias operators, which are grids here, right? So you have this grid delta that will be obtained, and then delta squared just square it, and so on. You can go to the order that you want in the bias expansion. And then basically you sample the bias parameters from the prior as well. And your deterministic model for the galaxy bias expansion is just going to be like each of these bias parameters, you define each of these bias operators. And the stochastic part, what you can do is just generate another grid, which is going to be a white Gaussian given by a certain power spectrum of shot noise, right? This little order that appears. And that's how we construct the galaxy density field grid. So it's really just the bias expansion. And in principle, this is valid to any cosmological tracer. So if you use this to analyze halos or galaxies, this should work. This is a choice that you make, right? It's not hard-coded. You just put the prior that you want. And again, this is active area of research, right? What do you choose for these priors? Usually what people say is that this parameter should be order 1. So you don't have to put a too big prior, but you know, it really depends on the tracer you're analyzing. It really depends which order this parameter is, depends, on several things. And also our parameters run with lambda, so this is also another thing. We can't just use the separate universe predictions directly. So yeah. But usually order 1, standard deviation. So basically, this running is, so because we have this finite cutoff of the grid, depending on the cutoff that we choose, the bias parameters will run a bit, right? Okay, I just should do introductions. So we don't care basically about it because they don't run so much that we see that like basically our cosmological constraints are in general unbiased. So we don't see also that the posteriors for many of the bias parameters are like, I don't know, touching the prior. I mean, at least to second order. So yeah. I think you don't need to really worry about this. The idea is that they will run so that cosmological parameters are unbiased. But if you want to use priors from a separate universe, like for example, how the third order depend on B1 and so on, then you need to. Yeah. So the first test that we did was analyzing Euclid-like mock data. And we were interested in seeing how the power spectrum by spectrum can break the genus of sigma 8 and bias parameters. And usually what we get is this huge corner plots where here we have this, we usually plot sigma 8 over sigma 8 fiducial, which we call alpha. So if you find this to be 1, you have bias difference. And this bias and stochastic parameters here we use actually Lagrangian bias expansion because we have both things, but doesn't really matter. And in this case here, we were interested in seeing, do you remember that I showed that there is this discrepancy like on very large scales between the distribution power spectrum by spectrum from a Gaussian? We were comparing like if this makes any difference for inferring sigma 8 in this case, right? For this red, this scale cuts and so on. And in this case, really this doesn't make much difference. Neither does if you use a sample analytical covariance. We also did some tests to see if, for example, our posterior is under or over the confident. This is called simulation-based calibration, and also convergence plots, because you don't want your posterior to depend on the number of simulations you use to train it, right? So what you can do is, for example, plotting the standard deviation of each of your parameter as a function of number simulation. Here we divided by Fisher so that just it's easier to see. you're not expecting your posterior from SBI to converge to Fisher, right? Because you're assuming your posterior is Gaussian, but this should give you a lower bound on their errors. So it's good to also for you to see if you're finding something that makes sense. So we didn't do yet analysis with more than one redshift, but what you would do is different redshifts, different beams. You could actually even stack everything in SVI because you're gonna learn the covariance and everything, right? Just stack our spectrum and all the redshifts, and then you need to have a set of bias parameters for each of them, right? So the next nice thing to do is to see if this is really working is now to, instead of using mock data that was generated from the same model as the observed data, right? We now use dark matter halos from n-body simulations, while the model we are using to train neural network is actually based on a perturbative Ford model. And if the bias expansion is correct and SPI and so on, this should give us unbiased results. And we tested two halo samples, SNG and U2, and two scale cuts. They differ in redshift and also in number density. And we found that in this case, we went to third order bias parameter. And I'm going to talk about this soon. And here again is our alpha sigma h over sigma h true. We found unbiased posterior and also that it matches Fisher really well. So it seems to also be working on dark matter halos as our first proxy of real data. And then you can ask if you can use this this technique to see how much the galaxy trispectrum you add to your as information to your posterior sigma 8. And what you wanted to see is whether this trispectrum helps you break in even further the degeneracy of bias parameters and cosmology. And so we are using this estimator here, where basically you pin over one of the diagonals. It was also used in these other works. And we did a lot of tests to see what was going on, if it was correct. So just for simplest thing you can do is a Gaussian random field and see if the trispectrum is 0, unless if it's a disconnected distribution contribution. We also tested the momentum dependence, so we can just generate here a Gaussian field and measure the trispectrum and compare it to the leading order expectations. And this seemed to be working really well. We started testing in some mock data. So these are the redshifts of the halo samples we're going to analyze later. And we saw that indeed the trispectrum has potential of breaking the degeneracy between these bias parameters and improving the constraints in sigma 8. So we tested also whether using sample or analytical covariance makes any difference for your posterior, and perhaps surprisingly, even for redshift 0.5 doesn't make much difference. And then we finally tested this on n-body halos, and as you can see here, the biggest source of information gain is by breaking degeneracy of B2 with other bias parameters in sigma 8. And if you plot the standard deviation, that will be things power spectrum by spectrum, true, with also trispectrum. For this case, we have like 1.3 to 1.4. So it's nice because we're finally able to assess how much the trispectrum can add information for this case here, testing n-body halos. And so this is a conclusion. I'm going to talk about something else now. So basically, we can do robust analysis by combining EFT and the bias expansion using LEFTfield. And this is really fast simulator. We can go to cosmological volumes, right? This is like using LPT, so it's really, really fast. instead of using n-body simulations that take forever to run. And then you're going to be worried if how many simulations you need for this to be converged. We saw that we need 10 to the 5 simulations for convergence, but we want to improve this number. And we were finally able to evaluate the tri-spectrum information content, in this case with SBI. And again, all of this without assuming a Gaussian likelihood or really any, you don't have to explicitly calculate the loops or the covariance. How much time do I have? Oh, okay, perfect. So nice, we saw that SBI allows us to circumvent some of the issues that I raised in the beginning. So estimating the covariance or inverting it, here we really just learn it from the simulations. Also, it's in principle easier to model these endpoint functions here without having to explicit calculate the loops. And yeah, we don't need to to assume that the likelihood is has a certain analytical form and be worried if this can bias our cosmological constraints. Sorry. Yes, yes, understood now, sorry. So this will depend on the cosmological parameter you're analyzing, your scale cuts, your redshift, your volume, and so on, right? But for this Euclid-like mock data that we tried here, here, we saw basically no difference for the posterior of sigma 8. In red is using the full distribution, including higher order moments. And in blue, we just sampled like by construction Gaussian distributed summary statistics X from the Ford model. And then we saw that basically there is no much difference in this case. How I do the explicit likelihood. So basically LEFTfield gives us a realization dependent endpoint function, right? You measure the endpoint function on a grid that has a certain realization. So what you need to do, I'm gonna talk about this a bit later, is that you, for a range of cosmology, you calculate the mean of these endpoint functions over realizations, right? For fixed cosmology and a range of it. And then you can interpolate this mean over cosmology, and then you have a model, and then you can here plug a covariance and just sample now from this mean that you learned from a certain covariance, and this will be by construction Gaussian with the covariance we chose. So either a sample or an weight covariance, for example. The covariance, we have the sample covariance is just we fix cosmology and bias and measure over initial conditions. And the analytical one is just the diagonal one. Yeah. Yes. Then you don't know exactly. Yeah. But I don't know, depends on the cosmological parameter, right? Maybe if your cosmological parameter is really sensitive to the low K modes, it could be that impacts even at higher Kmax. So yeah, the point here is just saying that we know that for the endpoint functions, this is a small effect, and this is what we expected. It's just that with SBI, you don't have to even worry about this, right? This is more the point. Yes, it is. It is much cheaper. If you're doing things smart, like if you normalize your input data, it's usually much cheaper. Yeah. because you're transforming it to Gaussian distribution, right? So yeah, exactly. But it's still, the SBI still learns the parameter dependent sort of, right? Yeah, exactly, which is what we expect. Yeah, yeah. The higher K max, the least the difference. Yeah. Yes. I have a backup slide on that. I'll go back to this after, because it's a bit more involved. So I'll go back to, if I forget to let me know. Here yeah, no, let me go back to this later. So, okay. We concluded SBI part, right? And then we were saying that we circumvent these issues. So the question now is, okay, let's say we were finally able to do trispectral analysis with SBI, which is not true yet, but let's say this, then what do we do next? Do we put the galaxy quadri spectrum, or like, but then you're basically gonna have the same number of beams as you have modes in your grid, right? So this doesn't make any sense. So what you can ask yourself is whether you can use this galaxy density field directly to do inference, which is field level Bayesian inference, and we can do that also using LEFTfield. The idea here is that you start from initial conditions and you have your third model to have your model for the galaxy density distribution. And now you can use the explicit likelihood in this case that I'm talking here about to do a comparison between your observed data and your samples. And then here is how our likelihood looks like. And the only thing that I want to stress here is that you're really comparing your observed data and your model voxel by voxel. Really what's entering here is k. So you can ask yourself whether this can bring you more information than, for example, compressing this density field to summary statistics. And then you can do to actually obtain the posterior of now not only your cosmology and bias parameters, but also the initial conditions, right? The value posterior for each of these voxels, which can like grows very quickly with the size of your grid. And this can be like order of 10 to the 5 posterior, right? This is really high dimensional. So we have to use Hamiltonian Monte Carlo, which is a sampling technique that is much more efficient for high dimensions. And it's nice because once you have the posterior of your initial conditions, you can do like, for example, tests of systematics and so on. And yeah, that's why people are usually interested in this. So we wrote this paper. Again, we have the same model, breaking the generosity of sigma 8 in bias parameters and rest frame, testing on dark matter halos. And the idea here was that, so here is what we have been talking, like the SBI pipeline, right? You have a LEFTfield generating delta G, you measure per spectrum by spectrum, near density estimation to obtain the posterior. And here's what I just introduced, field level Bayesian inference, where now you use delta G directly, right, to do cosmological inference. And then we want to compare the cosmological information between these two. And in this case here, we were going third order in the bias expansion, and our stochastic field was just Gaussian, right? So in principle, you are missing like a stochastic contribution in the bispectrum. And I'm gonna talk about this soon, but we wanted to do an apples to apples comparison, and the field level likelihood assumes that the noise is Gaussian. Otherwise, if you wanted to do with no Gaussian noise, you would also just have to sample the noise field. And this is just takes ages to run because it's such a high dimensional space, right? So that was the first. So this was an apples to apples comparison in the sense that we were using the same Ford model. the same data, right? Dark matter halos, and also the same scale cuts. And what we found is that you can have, in this case here, 3.5 improvement factor. This plot here is showing you the posterior of sigma 8 over sigma 8 true for field level inference in blue, and in orange for SBI that you will obtain with power spectrum by spectrum. And here was one of the dark matter halos that we were analyzing, and we tried for different scale cuts and also different halo samples, and we found a lot of improvement here. And then here we can also compare now with the galaxy trispectrum, for example, and you see that this is the error not on sigma 8. For power spectrum by spectrum had 0.17, and then when you add trispectrum, you have like 1.3, 1.4 improvement factor. And but there is still information even beyond the trispectrum, at least in this case that we were looking at. So this makes us excited to do field level inference. So some final thoughts here on SBI. How much time do I have? 5, okay, that's okay. So we found a lot of improvement factor, right, with the field level inference. So we were wondering, I don't know, is this our SBI error bars really reliable? So one thing that people usually do is comparing to MCMC. So we went down this road to compare to MCMC as well. And as I said, LEFTfield gives you predictions of the realization dependent endpoint function, right? So what you can do is that you can calculate the mean over realizations for each for discrete points in cosmology, and then you can interpolate this. And then your model for the theory to do the MCMC is just going to be really multiplying the bias parameters by this mean of the endpoint functions that you obtained from LEFTfield, and you interpolate it over cosmology. And then after is a bit, it takes some time to calculate all these endpoint functions over cosmology and realizations, but once you have it, it's really fast to run that MCMC because it's just matrix multiplication. And then we did comparison to MCMC, and it was interesting to see that this is one of the halo cases we analyzed. We saw that it matched pretty well with MCMC, so this was nice to see. And I wanted to also mention that there was a recent paper by Francesco and Marcos here in the audience. And it is very, very intriguing because they have a very similar model to us. So power spectrum by spectrum, redshift 0.5, and although they were doing Fisher analysis, should be very similar. And they found an error bar much smaller than our error bar for power spectrum by spectrum, right? And here, we like really doing power spectrum by spectrum analysis, you should understand this really well. So I think the devil is on the details. Like there are many differences in between both that you would naively think that they don't make any difference, right? So one of the things that was raised here is that in our work, we just take parts of the loops, right? This perturbative fork model, and you can ask if this is going to make any difference. While Francesco's paper, they actually do what is the standard in the literature, taking the tree, power spectrum tree by spectrum, and one loop by spectrum. Power spectrum. And again, so here we do SBI, they do Fisher, but I just showed you this BI is the same as Fisher and is the same as MCMC. So the inference method here is not the issue. Same thing here, non-Gaussian or Gaussian likelihood, we just thought this is not making any difference, sample or analytical covariance. So probably here, I think the main difference is coming from the parameter space, right? Because if you're using this model here, of course, 3 out of the 4 bias parameters are not going to appear in your model, right? There's just 1/3 order bias that appears in the one power spectrum. So simple test that you can do is here mock data, just a second order bias, and we find like even smaller error bars than them. There are some other differences here, like how we model the higher derivative terms and so on. But yeah, it's interesting to see that. And I think this comes down to really what do you want to compare, right? Is this an apples to apples comparison, really using all the parameters that you use in field level inference, or you just want a model that works and fits well your data, right? And yeah, we can spend hours talking about this. If you have any questions, you can let me know. Just something else that I wanted to mention is the fiducia values of these bias parameters seem to matter a lot. Here is the standard deviation of B2 as a function of the fiducia B2. And here's power spectrum by spectrum. Here is summary statistics called the Pareto correlator that Ivana will talk about next week. You can also talk to her. She's here the whole week if you're interested. And here is field level inference. So you can see that if you plot like this ratio here of information gain, it also depends on the tracer you're using. So we have to be also very careful when we are comparing both cases, because we also have like different bias expansion model and also different priors. So yeah, I think it's going to be nice to have a really consistent comparison between both cases. So this is the conclusion. It seems we're moving towards having finally SBI inference with using the FT. And this is really nice because we can do very fast inference on cosmological volumes and everything that I said. And also we saw that you can have a lot of information also at the field level. And yeah, we also want to include more observational facts, go to redshift space, and of course have more cosmological parameters. Like this was more trying to put these new inference techniques to work, and also explore more summaries in SBI as we are doing with Ivana. And that's it. Thank you. Yes, not the complete, like, not exactly what, like a one-to-one comparison to what they did, but I've been trying remove and include loop contributions and the posteriors change in a way that we don't understand completely. Like I didn't show here, but we can talk offline about that. And it's very interesting actually to see how including parts in our theory of the loops that you would expect to be higher order actually degrades your error bars. So yeah, this is something I'm still trying to understand. Yeah. Yes. Yeah, I was gonna put a backup slide on that. We did a comparison, but it seems to also have more information in redshift space. But again, this all this discussion, right? Depends on the parameter space you're considering and etc. But yeah, in some feature analysis we did was giving more information in the redshift space. If you level comparing to power spectrum and by spectrum. I don't remember. I can show you later. Mm-hmm. It's just like the bispectrum, right? You have k-min, k-max, and you choose the number of bins. And then this is gonna be the number of bins in all k directions. So k1, k2, k3, k4, and the diagonal. And you bin over all these things, and then you want to close a theta-hedron, basically. Yeah. Depends. It depends. Here, so for example, to do this MCMC and so on, I did a wider bin. So I can have order of like 500, so not many. But in principle, we want to have like close to K fundamental, delta K, so this can go to 10,000. Yeah, this can grow really fast. This can grow really fast. And what you can do is also to compress the trispectrum with some method. Like there is these methods like Moped, there is also neural network compression. And this helps a lot efficiency. Like I see convergence much faster with the compression. Yeah. I'm not sure for the trispectrum. I don't know. Is this a compression thing or? Okay. I never saw it. I don't know. You can show me later. Okay. Yeah, as I think you just have to reduce the dimensionality in a smart way, right? So that you don't lose information on your cosmology. Mhm. Yes. We don't know the true conditions of the true simulations. What we do is that we sample from the Ford model, and I mean the cosmologies of the both simulations are different, so of course it's going to be different the way you sample from the initial conditions. Was this the question? I'm not sure. It's always going to be a Gaussian random field with a certain power spectrum. And for example, the U2 and SNG simulations had different cosmology, so this initial power spectrum was a bit different, right? But it's just a Gaussian random field. Yes. Between what? You mean if you look at the posterior of the initial conditions? Oh, we sample completely independent, right? Just from the prior, and we fix all the cosmological parameters with except a sigma h to the true ones, because we are not sampling them, and in principle you also sampling everything independently. And then you do the sampling like this HMC, so that at the end you have a posterior that should be, yeah, correlated with the true. If you plot the cross correlation coefficients with the true initial conditions, then you should be matching if we're doing things correctly. And we did have the true conditions of SNG, so we could do this fixed phases analysis, right, where you fix the initial conditions and just sample cosmology, and then we would have like an idea what are the parameters. But for the two, we didn't know the initial conditions, so yeah. You want to ask some? Yeah, that's true. That's true. This is very useful. That's why you can do even wide binning without caring so much. You just do the same thing on the data and in your simulation, and you don't have to care about it. I don't know. Yeah, actually, this estimator here is actually integrating over one of the diagonals. So I think the first trispectrum estimator is this integrated trispectrum that um, integrates over both diagonals. And then this other estimator was proposed, which beams over one of the diagonals. And yet, there is still, as far as I know, not an estimator that also beams over this diagonal here. Maybe using some multiple expansion, we could do it. Mhm. Also power spectrum. Yeah, both. Yeah. Depends on the order that you go in the bias. Yeah. So what I'm doing now is like, because now I have the CMC, I can whatever I want to the model. So I like exclude or include the loop contributions of power spectrum or by spectrum. And because it's so fast, like, a minute or two, I can have loop posterior and then I can see how these higher order loops affect the posterior. And yeah, I still don't understand many of these things, but it's interesting. It's on the way, on the middle of the way.